Now, what's kind of strange so far about this section is that Rolle's theorem kind of seems weird. Why do I need to guarantee that there's going to be a time when I get a tangent line of slope 0, as opposed to just doing what we did at the end of example 1, which was, why don't I just find the times when I get a slope of 0? Why do I need to guarantee that they're out there and then go hunt for them? And that's a very legitimate question. What we're going to see is that actually the theorems that we have in this section, which are Rolle's theorem and the mean value theorem, are not necessarily going to be things that we are going to kind of directly use to help answer very specific questions. That is, like, I'm very rarely going to get a question that's going to say, use Rolle's theorem and show that you meet the conditions and find the values. That's not really the purpose of Rolle's theorem. Rolle's theorem is a tool that we can use to prove more complicated results. And we'll see how this works throughout this video as well as the next one. Let's take a look here really quickly at example 2 to see how we can use Rolle's theorem to show something very unrelated to what Rolle's theorem actually says. We want to go ahead and prove here that this equation has exactly, and that's a typo there, but this should say exactly one real solution, right? So show that there is exactly one x value that makes this work. No more, no less. Now we could obviously start trying to guess what the x value is, but that could take forever. And unless I know a way to actually easily solve this, I might be kind of stuck. So how do I use Rolle's theorem to show, to demonstrate that this has only one real solution? Well, first I'm going to go ahead and start by trying to show the following. I'm going to show that there is at least one solution. That's going to be my goal right now. I'm going to show there is an answer to this equation, right? There is a solution for this. And in order to be able to do that, I'm actually going to pull back on an old idea that we talked about in our very, very first chapter. Let's take a look here at what I'm going to do. I'm going to go ahead and say, how about I create a function here of f of x is x to the third power plus x minus 1. And right now I'm curious if this function can ever hit the y value of 0. Well, we know that f of x is continuous everywhere because it is a polynomial. Okay? So I'm also going to go ahead and note the following. Note that if I was to go to my function f and plug in 0, I get negative 1. And if I was to go ahead and plug 1 into my function, notice I get 1 plus 1 minus 1, and I get positive 1. Can you tell what theorem I might be making use of here? I found that I have a function that I'm interested in hitting 0 with. I know my function's continuous, and I know that I have a point ultimately that is going to exist below and above the y value that I'm trying to hit. Do you remember? This is the intermediate value theorem. If my function's continuous, then I have to cross this y value of 0 at some point. So, by the intermediate value theorem, there is a value of c in the interval here, apparently from 0 to 1, such that f of c spits out 0. So, we can then say that there is a value, right, that when I plug it into this function, I hit 0. And so what that really means is that the equation of x to the third power plus x minus 1 equals 0 has at least one real solution. Notice the only thing I can guarantee is that there is a solution. I can't guarantee how many there are. There might be more than one solution. All I know is that this graph has to cross over 0 at least one time, meaning there's some value I can plug into this formula to spit out 0. I also don't know what this value is, but I do know that it's somewhere between 0 and 1. I know it's there, even if I don't know exactly what it is. So if I think right now about what I've actually generated, I know that if I was to come up here and think about the number of solutions right now that there are to this equation, the number of solutions to this equation could have been 0, or 1, or 2, or 3, or kind of on and on and on and on and on. And what we've eliminated so far is that there can't be 0 solutions. That's impossible. There's definitely at least one real solution. So now I kind of have to get rid of the options of 2 solutions, or 3, or 4, or 5. So to do this, I'm going to go ahead and say that let's show there cannot be 2 or more solutions. This is going to be our next task, and this is where Rolle's theorem is going to really come into play. So I know that this equation here is either going to have 2 solutions and more, right? Like it either has 2, 3, 4, 5, 6, and on solutions, one of those values, or it only has 1. So let's go ahead right now and suppose that it actually has 2 or more solutions. So let's kind of pretend, let's experiment here for a moment. Let's suppose that x to the third plus x minus 1 equals 0 has 2 or more solutions. Let's just pretend, let's see what happens. Now, if there are going to be two or more solutions, then definitely we could say that there's going to be some value, maybe let's call it f of c1, and another value, say f of c number 2, that I can plug in to, well, let me rewrite that a little bit. So how about we say C1 and C2 are 2 solutions. Then we could definitely say, if we're using our f from up above, that f of C1 and f of C2 would both have to be values that spit out 0 when plugged into this function. And so if that's the case, now I can go ahead and I can start to see some things. Well, let's take a look at what we have. I can definitely state that this function here is going to be, let's see, first I can see that, let me rewrite this a little bit because that got a little sloppy, but I can rewrite this to say that I know that my function f of x is going to be continuous on the interval, let's say from C1 over to C2. Wherever those solutions are, I know that my function's continuous there, because again, it's a polynomial, right? No big deal. I could also state here that f of x is differentiable on this open interval from C1 over to C2. No big deal. Again, still the same basic idea. I have a nice simple polynomial here. Its derivative would be a polynomial, so it'll always be defined on these values. The function's differentiable there. And, of course, I can see that it's the case that whenever I plug in these 2 points, C1 and C2 into my function, they spit out the same value. Notice then, aren't these the conditions of Rolle's theorem? So because these conditions are met, I can say that, so, by Rolle's theorem, there must be a value of, let's just call it c, and it has to be in the interval between C1 and C2, where f prime of c is equal to 0. So there's got to be some value in between these where I could get 0 back. Okay, so let's go try to find that value. So I'll say, however, when we look to find when f prime of x is equal to 0, we see that f prime of x, first off, with my function here, is going to be a 3x squared plus a 1. And this is not able to be equal to 0, since this is automatically going to, or maybe I can write this a little a little bit differently. We see that what I have here, 3x squared plus 1, is there any value of x I could ever plug in here that would make this equal to 0? Notice that's actually impossible. So we could say, and this cannot equal 0 for any value of x. It's just not possible because 3x squared is always going to result in, at worst, 0 or maybe some other positive value. And then when I add 1 to that, I can't get 0 back. So something's wrong here. What we would say is that we've reached a contradiction. Essentially, there's an issue going on. So let me write this out here first. This is what we would call a contradiction. So the issue is, again, that we know that if our function has 2 or more solutions, then there's definitely at least 2 of them. And so we gave them 2 values. We know what it means for them to be solutions. Then there's got to be a function here. The function f has got to be continuous, differentiable. All these conditions seem to work. And Rolle's theorem must work. We proved that Rolle's theorem works. Anytime you meet the conditions, you automatically get a time when your derivative can spit out a 0. But since we're not able to spit out a 0 here, something's wrong. Well, Rolle's theorem can't be wrong, right? Rolle's theorem says if you meet the conditions, then it is a guarantee that you get the outcome. Well, that must mean then that one of our conditions actually isn't met. Like, we must have done something wrong, because otherwise Rolle's theorem should work. But we know our first condition's right because we can see our function right here. It's a polynomial. And we know that our function is differentiable because, again, its derivative is going to be a polynomial and can have any value plugged into it and always spit out something. So the only thing that's in question is maybe hypothesis number 3. Is it the case that f of c1 and f of c2 both equal 0? Notice this was the only part of the question that we couldn't really support. We just said, let's pretend. And so what we can state here at the end is that our initial assumption must be wrong. It's got to be wrong. There cannot be 2 or more real solutions. But if that's the case, right, if it's wrong to assume that there's 2 or more and that leads to problems, then that means that we've essentially eliminated all other possibilities except that there must be exactly one solution. So we can state that x to the 3rd power plus x minus 1 equals 0 must have exactly one real solution. So again, this is a very complicated example here, very, very complicated. But it shows you that Rolle's theorem is more of a tool. It's something that we can use, just like intermediate value theorem is something that we can use to help show a particular outcome. We're not necessarily interested in answering specific questions related to Rolle's theorem, but rather using Rolle's theorem in situations where it may be helpful.